Hello everyone, my name is Lianzhe Wang. In this video, I will be presenting our paper. Let's first have a 1-minute quick introduction with glancing at a poster. The generalization of meta-learning is crucial and challenging. Existing works focus on meta-generalization to unseen tasks, while ignoring that adapted model may not generalize to the task domains. In this paper, we propose a new minimax regularization method which employs ordinary regularization at the outer level and inverted regularization at the inner level. In particular, the inner level inverted regularization makes the adapted model more difficult to generalize to task domains. Thus, the meta model is forced to learn better generalized meta knowledge. Theoretically, we prove that the inverted regularization could improve the meta testing performance by reducing the generalization error, and extensive experiments are carried out to verify the proposed approach. Alright, after the brief overview, I will now proceed to provide a comprehensive introduction to our work. The title of our paper is Improving Generalization on Meta-Learning with Inverted Regularization at Inner Level. It is co-authored by Lianzhe Wang, Shiji Zhou, Shanghang Zhang, Xu, Heng Chang, and Wenwu Zhou. Meta-learnings focus on the performance of models on new unseen tasks, while the concept of generalization emphasizes a consistent performance of models between training and testing data. So, it is natural and crucial to consider generalization ability of meta-learning. Optimization-based method is one of the most representative approach to realize meta-learning. It formulates the learning process as a bi-level optimization problem. At an inner level, a base model, which is initialized using the meta model's parameters, adapts to each task with a support set. At an outer level, the meta model's objective is optimized based on the adapted model's predictions on task query set. However, for these optimization-based methods, the generalization challenges are twofold. One is meta-generalization, which means the meta model should generalize to unseen tasks, requiring performance consistency between training tasks and new tasks. Another one is adaptation generalization, which means the adapted model should generalize to the domain of the specific task, requiring performance consistency between task support data and true data distribution of corresponding tasks. Currently, there have been some works focusing on meta-generalization, while the adaptation generalization is typically overlooked. Therefore, in this work, we propose a minimax meta-regularization method to improve the both two levels of generalizations. The minimax meta-regularization combines two types of regularizations during the training. An ordinary regularization at the outer level to encourage the meta model to learn more generalized hypotheses, which is for meta-generalization, and an inverted regularization at the inner level to increase the generalization difficulty of adapted model, thus helps the meta model improve generalization during training, which is for adaptation generalization. Note that the implementation of minimax regularization could be quite easy, oftentimes only involves modifications to inner and outer level loss functions. Why inverted regularization at inner level may improve adaptation generalization? Intuitionally speaking, by making the adapted model more difficult to fit a meta support set, the meta model is pushed to learn better generalized meta knowledge. This can be seen as a form of adversarial training or loaded training for the meta model. You may draw an analogy to the real-world loaded training process of pro athletes to help understand its intuition. Importantly, we don't apply this inverted regularization at the testing phase. But anyway, the concept of using inverted regularization to improve generalization may seem either too intuitional or even counterintuitive. We provide a theoretical analysis to support this. In the theoretical part, We provide an analysis taking mammal algorithm with L2 norm regularization as an example. The regularization parameter delta can be either positive or negative to represent the ordinary or inverted regularization, and we treat delta as a variable and analyze how its value will influence the generalization error bound. Note that when we add regularization to loss functions, it also creates additional training bias while perhaps reducing the generalization error. Therefore, we need to consider both training bias bound and generalization error bound for analyzing the effects of regularizations. And let's drop tons of details and directly come to the results. The generalization error bound will look like this, and its property is that it monotonically increases with respect to delta, suggests that only inverted regularization may reduce the generalization bound. And the result of training bias bound suggests the inverted regularization has less corruption to training bias than ordinary regularizations. And the total test error bound suggests there will be a negative interval in which all values can be selected as inverted regularization parameter to improve the performance. Then, in the section of empirical analysis, we conduct extensive experiments on multiple datasets to verify the effectiveness of our approach. We first make an empirical verification experiment. The results are consistent with our intuition and theoretical results. Only inverted regularization at inner level and ordinary regularization at outer level can improve generalization performances. And the regularizations at the two different levels are compatible to each other and face different regularizers, like information entropy. Our methods also achieve promising results on the classic omniglot and mini ImageNet benchmark, and on a few short experiments challenging the generalization with limited training tasks. And also an experiment with larger backbones on the more complicated metadatasets, incorporating with the first-order meta-learning algorithm. To summarize, we analyze the challenge of meta-learning's generalization and propose minimax meta-regularization to address both meta-generalization and adaptation generalization challenges, with a special design of inverted regularization at inner level targeting at the adaptation generalization, with theoretical and empirical analysis to verify our effectiveness. On behalf of all the authors, I sincerely thank you for your time and attention for our paper. Thanks a lot.